Hi everyone, welcome to Physics Simplified. And as I promised that we will be taking a separate video on Catanary problems. So, I'm here with a problem containing the concept of taking differential elements in Catanary problems. Alright, so let's start with this problem. And so, first of all, let's understand what's a catenary. Okay, so catenary is a type of shape. Okay, if you do BSc in physics or something in classical mechanics, so you will learn a lot about this particular shape. Okay, you will do it, you'll solve it with Lagrangian mechanics and all. Uh, if you do BSc in physics, otherwise, I don't think that you will be doing it after JE and Pathfinder all. Okay, so this is a question of Pathfinder. Like, check your understanding. Question number third. I can write check your understanding, question number third, and little bit tough side, little bit on tough side. Okay, so if this comes in J advanced, then I can assure you that 99 or 100% students, 99 or 99.5, 99.8 or 99.9% students would not be able to even understand what's going on this problem. Okay, so take advantage of this, and if somehow this question comes in your paper, then you'll be in much advantage side. Okay, so let's start with this question, and what's this question is saying, and how you decode this question. Just under that, and just understand that. Okay, so I'm taking the general case. I'm not just solving this particular problem, but I'm taking a general case of catenary problems. Okay, so how will approach this? Just see my approach. Okay, so I'm taking a differential element of length dl somewhere here. Okay, no problem. All right, so I took a differential element. Just follow me. Okay, so this is a curve. I took a length out of it, and I'm just drawing the FBD of this here. Okay, so the thing is given that this whole catenary is in equilibrium. Matlab, it means that every point on the catenary is at rest, or we can say in mathematics term that every point on the catenary has net force, or F vector net is 0, right? Net force on each point of the catenary is 0. Okay, so if I take any 2 points, if I take any point or any you can say any figure, okay, and I take it out and I make the FBD of that particular figure, then net force on that particular figure should always be 0. Okay, so I took a differential element of length dl. Okay, so I hope you are mastered in this, that in such cases we take a differential element of length dl. All right. Okay, so the length of the differential element is dl. Okay, so I'm not writing it because of my page constraint. Okay, okay, so just see this, like we know first concept is that tension, right? uh, we show tension at any point on a curve as tangent to that particular point on the curve. Okay, so if this is my curve, so tension at this point would be tangential, something like this. Okay, understand? And tangent at this point would be also be tangential, something like this. Okay, so this is not okay, so I'll make this again. Yes, understand? I hope you understand. Okay, all right. So, and one more thing, that the variation in the tension would also be very small, as I have told earlier when we were studying NLM, and we did a question. I hope you guys remember, of Irido or Pathfinder something. We took the same concept, right? That if my tension here is T plus dt, then here it would be T. All right, my tension is increasing as I am going up the slope, or up the out at the point B or point A from this bottom point. Okay, all right, so you can understand in another way also that the okay, so I guess it's sufficient. I'm not just complicating it again and again. Okay, so just see it. And one more concept which you need to know in the case of catenary problems, that taking angles, how we take angles is very important in it. Okay, with the horizontal. Okay, so if I take, I'm just first telling and then I'll prove it why I'm saying this. Okay, if I take this angle as theta, okay, then this angle would be theta plus d theta. Then this angle would be theta plus theta. Okay, so I'm now explaining it how I did this. Okay, so there's no geometrical relation which I can find here, but by using simple logical approach, I can say that if this was my straight line. If this is my straight line and I talk about the angle of the straight line with the horizontal is theta, then it's from here also it should be theta, right? Right, alternate interior angles. All right. But now what happened here is, now this is not a straight line. This pink length is not a straight line, but this is a like a length which is almost a straight line. Not a straight line, but almost a straight line. But almost a straight line. Okay. And the curve, okay, like we took a differential element here. Okay. Just understand this, that we took a differential element here. Okay. So this length is so small that the variation in the angle is also very small. You can understand in like, you can understand that, okay, that the length of this differential element is so small that the variation in the angle from bottom to up with the horizontal is also small. All right. So variation is what change. Okay. So if this is theta, then this should be also theta plus d theta. All right. That's the smallest change I can get. Okay. Or I can write in mathematical terms. Okay. So now let's proceed further. So I hope you guys understood what I wanted to say from this concept. Okay. All right. So now I just told that this whole catenary is in equilibrium. Then every point on the catenary should also be in equilibrium. Then this differential element should also be in equilibrium. Okay. One more thing, that this is given that this length is uniform. So I can take this lambda is uniform. Lambda is linear mass density. Okay. Okay. So I can write that weight of this is lambda lg, sorry, lambda dlg. I'm not taking length because this is a small length dl. So lambda dlg. Understood? This is the weight of this rope. Okay, so now this whole differential element of length dl is in equilibrium. Okay, so I just balance my forces in vertical and horizontal direction. So taking vertical and horizontal components of this t plus dt and vertical and horizontal components of this t, and then balancing it. Okay, wait. Yeah. Okay, so what's the vertical component? So I can say that my weight is acting downwards, and there are only two forces which are acting, and those two forces are also opposite to each other, right? So they, here is like t plus dt cos of theta plus d theta, and here it is t cos theta. All right. So can I directly equate these two forces, because the net force along the horizontal should also be equal, and there are no more forces which are acting in the horizontal direction. So I can just directly equate these two forces, right? So okay. So equating these two forces in horizontal direction, t cos theta should be equals to t plus dt cos of theta plus d theta. Understand? Okay. So one more concept which you will require to solve, to proceed further in this problem, is if I take small angle approximation. Okay, small angle approximation. So if I take uh, a very small angle inside the function of sine, like let's say sine d theta, then I can directly write it as d theta. All right. And same for cos, I can write it as 1. All right. So I hope you don't need any explanation of it, and you can just mug it. Okay, just mug it. It's the proof of this is not that much important in physics. You will just learn it in maths in class 12th. All right. So just let's open this by using cos of a plus b formula. So t plus dt. Okay, I'll just shift it a little bit downwards so I can get more space. Uh, t plus dt into cos. Applying the cos of a plus b formula, which is cos a cos b. Cos of d theta is 1. Cos a cos b minus sin a, and sin of d theta is d theta. Understand? All right. Is equals to t cos theta, is equals to t cos theta. All right. So just multiply it. It's t cos theta minus t sin theta into d theta plus dt cos theta minus dt sin theta into d theta is equals to t cos theta. All right. Now one more thing you will learn from this problem or from this step, that product of these two infinitely small numbers. What is dt and d theta? Dt and d theta are two infinitely small numbers which are tending to 0. So product of these two infinitely small numbers is always 0. So okay, so just remember it from now onwards that product of these two infinitely small numbers or three infinitely small numbers is always 0. Okay, so from this you can cancel t cos theta and t cos theta. So from this you get dt cos theta. Wait, dt cos theta is equals to t sin theta into d theta. Alright. Okay, so I hope you have understood this part. Now we are left with vertical portion. Okay, this is our equation number 1. Call this as equation number 1. Now balance this in vertical direction also, because you know that this whole my differential element is in equilibrium, because my whole uh, catenary is in equilibrium. So just take the vertical components of these two. What's the vertical component? T plus dt sine theta plus d theta is equal to, now add weight also, because weight is also acting downwards. Okay, okay, just don't forget it. Okay, okay, so I can write it like, just see, like t plus dt, t plus dt, t plus dt, okay, t plus dt sine of theta plus d theta, sine of theta plus d theta is equals to lambda dlg plus lambda dlg plus t sin theta plus t sin theta. Understood? Okay. Now again, just open sine a plus b using sine a plus b formula. So it's t plus dt into sine a cos b. Cos of d theta is 1 plus cos theta into sine d theta. Sine d theta is d theta plus cos theta into d theta is equals to lambda dlg plus t sin theta. Alright. Now multiply these both. So it's t sin theta plus t cos theta into d theta plus dt sin theta, or plus 0 because of this. There are two infinitely small numbers which are getting multiplied, so product of these two infinitely small numbers is always 0. Okay, alright, is equals to lambda dlg plus t sin theta. Alright, so just cancel these both to t sin theta, and you are left with, again, just see it, t cos theta into d theta, t cos theta into d theta plus dt sin theta is equals to lambda dlg. Alright, okay. So just take dt sin theta to the right, and now let's see what we are getting. What we are getting, t into d theta into cos theta is equals to lambda dlg minus dt sin theta. Alright, so this, call this as equation number 2, and just uh, put it under bracket. Alright, so this bracket is just messed up. Okay, so now substituting the value of dt, substituting the value of t theta from equation number 1 and putting it in equation number 2, we'll get a following equation. So let's solve that particular equation, or let's just find the value of t theta, and we'll just equate both this t theta. Okay, t into d theta. What we're getting, t theta is equal to dt cot theta from here, from equation number 1, right? Okay, now from here we are getting t into d theta as uh, I'll directly write it as cos theta. Okay, understand? Okay. So I'll just equate these both two equations, equation number 3 and equation number 4. Sorry, equation number 3 and equation number 2. Okay, so dt cot theta, dt cot theta is equals to lambda dlg minus dt sin theta by cos theta. Alright, so it's the same thing. So just multiply cos theta here, dt cos square theta by sin theta plus में dt sin theta is equals to lambda dlg. Alright, so dt Okay, just give me a minute. dt cos square theta plus dt sin square theta uh, by sin theta is equals to lambda dlg. Okay, so I'm left to do upper dt is equals to lambda dlg sin theta. Lambda dlg sin theta. Alright. So I guess now you will solve it further and you will get, and from now just integrate it from t1 to t2 and you will get your answer. Okay. Yeah. Just let me check it again. I hope there are no problems. Uh, cos squared theta and cos theta by sin theta, cos squared theta by sin theta plus sin squared theta. So it's sin theta and okay. So this is our correct equation. Here lambda is constant, your g is constant. Okay. Try to find dl in terms of sin theta. Try to find dl in terms of theta and then integrate it, you will get your answer. Okay. So that's how you approach a particular catenary problem. And the second part which is asking is radius of curvature of the rope at the lowest point. Okay, so you have to find radius of curvature at the lowest point. What is the lowest point of this catenary? You will see the lowest point of this catenary is this. Okay, so my students know that this catenary will have something equation called y is equals to f of x. Okay, it will have, but it is not given in that in this particular question. So how we will approach the radius of curvature formula of radius of curvature type question? So just see, we know that if we had a particular equation relating between y and x coordinate of that catenary, then we can just directly use that formula of radius of curvature is equals to 1 plus dy by dx ka whole square is ki whole power 3 by 2 divided by d square by dx square. But to do dy by dx, we need that y is equals to f of x. But it's not given in this question. That's what make this question of Pathfinder and not of any particular local coaching module level run. Okay, so now let's take a differential element at the bottom point. At the bottom point, that's what I can do. Okay, take a differential element at this bottom point. So I'm taking, okay, so I took a differential element at the bottom point of length dl. This is my center and okay, yeah, okay, yeah, very good. Okay, so now we know, जैसे हमने ऊपर भी देखा कि we'll have tension in tangential direction of the curve at any point. So this would be my tangential. Okay, all right. Okay, okay, okay. And we also know by geometry that my this angle, okay, wait, yeah, my this angle is d theta by 2 and this angle is also d theta by 2. We have did this geometry many times, right? So I hope you have mugged this geometry d theta by 2. All right, okay. So now we know that this whole catenary is in equilibrium. Okay, so this bottommost point, so so the differential element of dl length of this bottommost point should also be in equilibrium. Net force should also be 0. Okay, so I'm taking, because this is a like this is not a light rope or a massless rope, this is a mass rope. Okay, mass rope. So this rope has certain mass, so tension will vary according to the x coordinate or according to the length of, as I increase or decrease the length of that particular mass, so tension will vary. Okay, so let's take this tension as T1 and T2. Okay, so balancing this equation, you'll get that T1 is equals to T2 in horizontal direction, and in vertical direction, as this is lambda, as this is dl length, so I can write that weight of this length will be lambda dlg, as we did in previous slide. Okay, here we did right lambda dlg, so it's the same case. Okay, and we will have a perpendicular component also of these two tensions. How? Now as T1 is equal to T2, so I can take that these both are T2, so this is T1 sine d theta by 2, this is also T1 sine d theta by 2, so I can just add and it should also be in equilibrium. All right, so okay, One more thing, how will I put my radius of curvature in this equation? Because how will I like how will I just uh, take that radius of curvature term in my equations? So see, just see it. Okay, you know that this is the center. This is center of that particular sphere which will form at the bottommost point of that catenary. Okay, so if I take this as radius of curvature, okay, this will be my radius of curvature. All right. So by using theta is equals to L by R formula, this whole angle is my d theta. Okay, so by using this formula, if this is my arc length, okay, and this angle is d theta and this is ROC, so I can write this dl length in terms of ROC, right? So what will I write is theta equals to L by R, so dl is equals to ROC into d theta. Okay, so I can write it as lambda ROC into d theta into g. Understand? So just equate t1 sin d theta by 2 and t1 sin d theta by 2. Twice of t1 sin d theta by 2 is equals to lambda ROC d theta by g, d theta into g. Okay, so क्या आ रहा है मेरा? Just see it. 2t1 sin d theta by 2 is equals to lambda r d theta into g. Now we know that there's a very small angle inside the trigonometric function of sine. So I just take it out and I can write it like t1 into d theta is equals to lambda r d theta into g. So I cancel d theta. So I am ending it with t1 is equals to lambda r g. Alright, and that's also my t2 also, because t1 is equals to t2. Understood? Okay, so from from here you will find t1 and then you will end this uh, whole question. Okay, so that's your catenary problem, and that's how you analyze a particular catenary problem or any problem with a type of mass or bend in a particular shape called catenary. Okay, so that's it for today. Thank you for watching this video, and I hope you have got some useful knowledge which will get applied in any examination in which you will appear. Okay, so that's it for today. See ya in next video. Take care.